Everyone knows what a magnet is. Magnets are essential components for many devices that are used in everyday life. We use magnets when we pay for our food, gas, or anything really that we use our debit or credit card.
Most of us know that magnets have two different poles.
We know that like poles repel and opposite poles attract.
However, this does not make it clear how a magnet really works.
Now, why is it that some components are magnetic while others are not? And why are some substances magnetized by a field while others are not affected?
Well, in order to give answers to such questions, we need a microscopic understanding of magnetism.
As the smallest particle of an element, it is made up of protons, neutrons, and electrons. Magnetism at the atomic level is largely due to particles called electrons. A magnetic field forms around the wire when current flows through it. Current comes from a bunch of moving electrons. The magnetic field is made up by these moving electrons. The electric current turns off, the magnetic field around the wire will disappear.
The mechanics as to how a magnet really works breaks right down to the atomic level.
Every atom or molecule has potential to be magnetic since it depends on the movement of electrons.
These electrons move in two ways. They spin and orbit.
For a long time, electrons were believed to orbit a nucleus, much like planets orbiting the sun.
The spin and orbital movement give rise to magnetization, which is similar to an electric current circulating a coil and producing a magnetic field.
The spinning of the electrons therefore defines the direction of magnetization in a material.
If all the magnetic moments inducing the material are in the same direction, then the material behaves like a magnet, without any application of the external magnetic field. But if all the magnetic moments inducing the magnetic material are in different directions, then they cancel each other out and the resulting becomes zero. In such cases, the material does not behave like a magnet.
To make such material behave like a magnet, we need to apply some external magnetic field onto them.
Thus, we can say that the atomic origin of magnetism in any magnetic material can be explained by taking into consideration the magnetic moments of the spinning and revolving electrons.
Paramagnetism is a type of magnetism that is due to unpaired electrons. Due to this unpairing of electrons, a kind of permanent dipole moment arises. Paramagnetic atoms are attracted to a magnet. Unless an external magnetic field is implemented to it, a paramagnetic substance has no magnetic field. Examples of paramagnetic substances are aluminum, platinum, copper sulfate, and oxygen. This is because these substances are weakly attracted in the presence of a magnetic field. With the figure on the left, we are able to see how the magnetic dipoles are randomly oriented and there is no net magnetic dipole moment associated with the material. This is with the picture in the absence of the magnetic field. However, with the figure on the right, we are able to see a collection of magnetic dipoles completely aligned with the field, and this is the picture in the presence of a magnetic field.
Ferromagnetism is the strongest type of magnetic behavior and is the most common type of magnetism. Some ferromagnetic substances include iron, nickel, cobalt, and rare earth metals. These substances exhibit attraction to magnets and can be magnetized. The magnetism in ferromagnetic materials is caused by the alignment patterns of their constituent atoms. However, all ferromagnets lose their magnetic field if the temperature is high enough to cause their atoms to position in a different direction. An important feature of ferromagnetics are the domains. A magnetic domain is the region within a magnetic material in which the magnetization is in a uniform direction, meaning the individual magnetic moments of the atoms are aligned with one another and point in the same direction, but the magnetization of different domains may point in different directions.
Diamagnetism is an induced magnetic field in the opposite direction to an applied external field. In fact, all materials show a diamagnetic effect. An external magnetic field is applied to the material by two magnets. The external magnetic field causes the electrons in the material to change course. The new motion in the electrons generates an opposing magnetic field. This causes the material to be repulsed by the magnet. For example, helium. Its electron configuration is 1s2, so it has 2 electrons in its s orbital. It has paired electrons, so it's diamagnetic. Another example is neon. Neon's electron configuration is 1s2, 2s2, and 2p6. As you can see, all of its electrons are paired. Therefore, it's considered a diamagnetic material. Another common example is water. In the picture, you could see water's molecular orbital. Similar to the previous examples, all of water's electrons are paired. By having all of its electrons paired, it will not be magnetized, but it will be repelled by an external magnetic field. Thus, water is diamagnetic. The best diamagnets are superconductors, as they completely expel the magnetic field from the material. In addition, any diamagnetic material will levitate in a strong enough magnetic field. For example, this frog levitating in water. Water is diamagnetic.
The basic law of magnetism states that like poles repel each other when coming into contact with one another. As you can see in the picture to the right, when the north pole of one magnet is brought near the north pole of the other magnet, the magnets repel each other. Below that, we can see that when the south pole of one magnet is brought near the south pole of the other magnet, we see how they also repel each other.
The basic law of magnetism also states that opposite poles attract when they come into contact with each other. As you can see in the picture to the right, when the north pole of one magnet is brought near the south pole of another magnet, we see that the magnets have an attractive force towards each other.
Ampere's law plays a major role in magnetism laws. Ampere's law can give us an infinitely long straight wire's magnetic field. The magnetic field lines around a long wire carrying an electrical current produces concentric circles around the wire. The magnetic field direction is perpendicular to that of the wire and is in the direction the fingers of your right-handled curl if you wrap them around the wire with your thumb in the direction of the current.
Permanent magnets are those magnets that we are most familiar with, such as bar magnets or magnets hanging onto our refrigerator doors. Permanent magnets align in the same direction, and their magnetic fields are created through currents. These currents are atomic currents. Essentially, are due to electrons spinning in atoms. These currents are always there. Electromagnets differ from normal magnets in one major way. Electromagnets can be turned on and off, which means that they can be controlled, and electromagnets are produced by the electric current and magnetized core. The strength and force of this electromagnets can be hundreds or even thousands of times larger than that of a permanent magnet. An example of a power source in this case would be a battery. The magnetic field of Earth, also known as the geomagnetic field, is a field extending from the interior of the Earth to where it meets the solar wind. This magnetic field is slightly tilted from the axis of the Earth. This magnetic field is also thought to be caused by the movements of the Earth's outer core fluid, mostly made up of iron and nickel. In reference to magnetism, Earth also behaves like a bar magnet, with the direction of the magnetic field pointing relatively from the geographic south to the geographic north. The geographic North Pole is a magnetic South Pole. A compass needle's North Pole is a magnetic North Pole. It is attracted to the geographic North Pole, which is a magnetic South Pole. The opposite magnetic poles attract one another. One major difference between that of a bar magnet and the magnetic field of Earth is that over time, Earth's magnetic field changes direction. This magnetic field makes a compass point either to north or south. It helps to protect the planet from the harmful rays of the sun. Earth's magnetic field also interacts with the solar wind and functions as a shield to protect Earth from disruption to solar particles.
Magnets are all around us. The compass is a great example of a magnet. It is used for navigating.
Follow us.
The compass is leading us to our destination.
The telephone is a simple yet important part of our modern culture. It relies on the interactions between permanent magnets and electromagnets to translate electrical information into physical sound waves. Hello? Like we said earlier, magnets are all around us, even in our computers or laptops. Watch this. Cool, right?
A good example of a magnet is a refrigerator. The magnets stick the paper to the door with its attraction to the metal in the door. In physics, magnetism helps to study the behavior
Of matter in magnetic fields. It's a great example of a magnet. Magnetism at the
credit card. Which I talked about. Okay. In physics, magnetism helps. Magnetism. I can't say magnetism. What even? Magnetism. Magnets are essential.